Okay, hello everyone. Let's proceed with topic 6, Karnaugh-Maps. So let's go straight into it. So this is the overview of our lecture for this week. We're going to cover the K-map methods to do Boolean simplification. So basically we're going to look at the logic minimization methods, 4 variable K-maps, simplification rules, don't care K-maps, and also K-maps for Maxterms. So what is actually a Karnaugh-map, or sometimes can be abbreviated to K-maps, sometimes called the K-maps. So K-map is basically a two-dimensional truth table where certain logic simplifications can be easily recognized. It results in an expression is guaranteed to be the simplest. Okay, so it's basically guaranteed to be the simplest in the Boolean equation. Is efficient up to 4 input variables, although 5 and 6 variables are also possible. And for 5, 6 variables we are not going to cover in this class. We are going to look at Boolean equations with 4 variables, 4 input variables and a single output. For the 5, 6 variables, normally people use something called the cube method. So this is a more advanced logic simplification. For more than or equals to 5 variables, we use the cube method. So let's have a first look at our K-map here. So here is a 2 variable K-map, and for a single output f. So for example, if we have a function, a Boolean function f with the input AB, this is our K-map. And if we have a function of f in terms of A, B, C as our input, then we have a 2x4 K-map. So in K-map we have the inputs here. So these are the inputs, A and B, and here is the value of the inputs for A. So this is for A and this is for B. And inside here is your output, F. Okay, so similar to the 3 input, we have the input ABC 0, 1, and here is BC. So BC 0, 0, BC 0, 1, BC 1, 1, BC 1, 0. And notice here that our BC11 is on the third column and not in the final column. So it's a 0, 1, 3, and 2 in decimal. Okay, so let's look at the example here of how we can use a K-map to perform a Boolean simplification. First of all, we need to fill in our K-map. So to fill it in, we first need a truth table. So here is our 2-input truth table function. And the output is just 1101. So what we do is we have the input here A and B, and we see that if our input is 0, 0, which is here, our input AB is 0, 0, then we have an output of 1 here. Okay, so we have the output of 1. Similarly, let's say down here, if we have an input of 1, 0, let's say 1, 0, so we have and here we are looking at 1, A equals to 1 and B is equals to 0 is here, and our output is actually 0, so we're going to put 0 in our K-map. So complete the table. So we have a 1 here corresponding to this 1 and 1, and that will be our K-map entry. So here is a min-term representation, which is sum of M 0, 1, 3. So 0, 1, and 3 here. Okay, let's look at the 3 input K-map. So here is our TT, the truth table, TT. Our K-map here is our K-map. Okay, 3 bar K-map. So it goes to the 4x2 K-map. Here is our input ABC, and similarly to the previous example, we are going to take, for example, we'll take one example here, 1, 0, 0, 1, 0, 0. And we are going to get, so 1, 0, 0, so we need to find, so A equals to 1 is here, BC is equals to 0, 0 is here, and our output at that time we have 0. So we put the 0 there. Let's make another example here, 0, 1, 0, so 0, 1, 0 for BC, 1, 0, and we have the output F equals to 1 is right there. So from the truth table, we can just transfer the data or the values from the truth table into our K-map. Okay, so from the specs to K-map, that's the first step. Get the truth table first, that's number 1. Okay, get the truth table, and number 2, we fill in our K-map according to our inputs. Okay, according to our inputs, and inside here is our output F, or single output F. So once we have filled in the K-map, the next step will be from Boolean. Okay, so here is another example. If we don't have a truth table, we need to convert to a canonical SOP first, then only we put it inside the K-map. So let's look at the example here. Given F equals to AB plus AC, and this is non-canonical SOP. We need to convert this to the canonical SOP, as we've seen in the previous video. We're going to use the complements theorem. So here's our complements theorem. Okay, whereby we are going to multiply or AND, rather, AB and C plus C bar, where C plus C bar here is actually equals to 1. B plus B bar is also equals to 1. So plus AC B plus B bar. Okay. And from here we can see that ABC, we will get ABC plus ABC bar. So we get ABC plus ABC bar, ABC plus AB bar C, AB bar C, and we see that this term here and this term here can be cancelled out because they are the same, and therefore we have AB bar C plus ABC bar, which is this one, plus ABC, the one term that we have cancelled out, and therefore this one is simply in the min term form is min term of 5, 6, and 7. So 5 and 6 and 7 is actually here. So here is actually 1, 0, 1. So this is 5. This is 1, 1, 1, which is 7, and this one is 1, 1, 1, 0, which is 6. So here is our min term 5, 6, 7. We are going to put inside our K-map, and we are done with the entry. Okay, so that is a method. If the truth table is not given to you, then you need to convert it to a canonical SOP form first, then we transfer the values into the truth table. Okay, so let's see, why does K-map work to perform Boolean simplification, and we have the complements theorem here. So for example here, if this part here, okay, so this part is actually A, B bar, C, okay, which is this one, and this part here will be A, B, C, okay, A, B, C, which is this one, and we can see that we can actually factor out our B bar plus B. Okay, we can factor those out, B bar plus B. So from here, we know that B bar plus B is actually equals to 1, and therefore this part here is in fact AC. Okay, so now this 6 literals, so we have 6 literals here, and now we have simplified it simply into 2 literals only. Okay, using the K-map method. So let's see more examples here on how to utilize or how to use the K-map. Okay, so let's have a look here. So in this example, we have assuming here is all 0, assuming that is all 0, we have a 1 all the way down there. So from our equation, Boolean equation, or the truth table, we have managed to fill in our K-map. So the next step is to find the output F given the K-map configuration. So what happened here is basically we want to group power of 2, using certain rules, with certain rules, and with the rules will go on later on. But basically what happened here is here we have we are going to group this together, okay, all the ones together, and we're going to call this F equals to A because A here equals to 1, okay, and therefore our F is equals to A. Okay, let's look at the next one. The next one, we're going to group again. We're going to group the 4 together. We're going to group all these together, assuming these are zeros. And from here, we can see that what is the common common literals there. Okay, so what is the common literal? So we can see here that in fact A here is not common, is 0 and 1, and C is also not common because the C here got 0 and 1, and the common here is actually your B. So you can see your B here is actually 0, 0, and therefore F is equals to B bar. Let's look at the next one, the next example here. So we can see A here is not common, is 0, 1, they are not common. The B is also not common. You can see the B here is 0, 1. Okay, here we assume these are 0. We're going to group this, we're going to group these 4 together. And from this grouping, A is not common, B is not common, and we see that C here is 0, are common, and therefore our F is equals to C bar. Let's look at the next one here. So here we are going to group, so these are all zeros, we're going to group these two together into one group. And what is the Boolean equation there? So what is common here is that we can see that for both of these, for this group, A is common, which is A equals to 1. And for this group also, we can see that C is actually not common because it's 1 and 0, but B here is common, 1, 1. So you can see that B there is 1, 1, A equals to 1, therefore F is equals to AB. Let's look at the next one here. Again, this is 0, this is 0. And from here we can see that A here is not common. Okay, here A here is not common, but our B, C are both common, and it's B bar because B is 0 common. C is a 1 common, therefore your F is equals to B bar C. And let's look at the last one here. So again, these are 0, and in this case we have no choice but to group only by itself, the logic 1 all by itself. And what is common here? The common is 0 here, 1 on the B, and 0 on the C, and therefore we have A bar, B, C bar. So what is the rule in the simplifications? Rule number 1 is the loop or cover all minterms in square of power of 2 as mentioned. So only group in 1, 2, 4, 8, and so on. Okay, you are not allowed to group in 3, in 5, or in 6. Okay. If the minterms may be grouped more than one way, choose the biggest and simplest loop. Okay, so there might be a case in the K-map that there are many ways that we can make the loop. So we want to find the biggest and the simplest loop. Minterms already covered may be reused. Okay, but if it's possible, we don't want to reuse it. If it's not possible, we may have to reuse the minterms. The next one, the Boolean function is complete when all the minterms are covered. So it has to cover all the logic 1 minterms in order to obtain the correct output F. Let's look at more examples here to better understand the K-map. So in this example, simplify this Boolean equation. So given this Boolean equation, there's two ways. We can simplify using Boolean algebra, which is challenging, or we can use K-map. So here we are using the K-map method to simplify the Boolean algebra. So written in canonical SOP form, here is actually 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 0. Okay, so here is actually 0, 1, 2, 4, and 6 in the minterm form. So 0, 1, 2, 4, 6 we can just transfer into our K-map, or we can also generate the truth table. So from the truth table we can see here is actually 0, 1 in decimal. So in decimal 0, 1, 2, 4, and 6. Okay, and where is 0, 1, 2, 4, 6 in the K-map? So here is 0 here, 1 here, 2, and 4, and 6. Okay, so 0, 1, 2, 4, 6. So make sure you have all the ones, okay, and the rest will be 0. Okay, so all the ones, so we can transfer from the minterms, or from the equation itself, or from the truth table, whichever way we prefer. So from here, so once we have generated our K-map, the next step will be to find the function f, the simplified function f, And from here we can see that we can actually group these together, and this is in fact C bar. Okay, so how do we know C bar? The 0 and 1 here is not common, and we see that the C0 here is the same. Okay, so we have both C0. B here is 0 and 1, so they are not common, they are not the same. So therefore, the first group there will be C bar. Okay, let's look at the second group. The second group here, we still haven't finished because there's the one here is not covered, so we are going to take this as our second group. And what is this? This is simply going to be A bar and B bar. Okay, the common bar, A, B bar. Therefore, your F here is in fact equals to A bar, B bar plus C bar. And this is equivalent to the original, equivalent to our original Boolean equation, which we have simplified now using the K-map. So that's the goal of the K-map, to eventually obtain the minimum Boolean expression from a canonical Boolean equation. So let's extend some more here, looking at the 4 input. Okay, the largest K-map that we can do, a 4 input Boolean. So in a 4 input Boolean, we have a 4x4 K-map. So here's a 4x4 K-map. Similarly, we have A, B, C, D. Just need to be careful here that AB11 is on the third row and CD11 is on the third column. So let's look at some examples here. So assuming all the others are 0, so if we group 8 minterms together, we group the 8 minterms together, and what is common here, we can see that B is not common because it's 0 and 1. CD is also not common. Okay, and therefore we can see that A0 here, therefore your F in this case will be F equals to A bar. Let's look at the next one. So the next one here, we are looking at 1, 1 there. So 1, 1 we have AB common, and then we also have C common, D is not common. Okay, and therefore your F is equals to ABC. The next one, we can see here that C, D are both common. A, B, they are not common, and therefore your F is equals to C bar, D bar. Let's look at the next one here. So we group these together. If we group these together, we are going to get A common, 1, 1. Okay, B here is not common, 1, 0. And then our D here is a common 0, and the C here is not common, and therefore your F is equals to A, D bar. Okay, let's look at the next one, F equals to BD. So if we group these together in the middle, we can see that the B here is equals to 1, A, 0, 1 not common, and then the D is 1, 1, C is not common, and therefore is F equals to BD. So the next one, the next one we can also group in the corner. So if we group in the corner, we are going to see that B is common, 0, 0, A is not common, and here we can also see that the D is common and the C is not common, and therefore your F is equals to B bar, D bar. Let's look at the example here. Given the K-map, okay, what is the minterm? Okay, for example, we can give this the K-map. So what is the minterm? The minterm is simply this is 2. Okay, 0, 0, 1, 0 is a 2, and then here is 0, 1, 0, 1 is a 5, and here is 1, 1, 0, 1 is a 13, and here is 15. Okay, here is 9, 1, 0, 0, 1, and then 1, 0, 1, 1 is 11. Okay, and therefore we have the minterm for 2, 5, 9, 11, 13, and 15. And from here we can also get what is our simplified Boolean equation, what is our canonical. So our canonical is this one. This is a canonical form. But what is our simplified F? Okay, so F is also equals to A bar, B bar, C, D bar, getting from here. So A bar, B bar, C, D bar, plus this one, will be B C bar D plus so here B C D C bar D, we get B here, and then C bar D there, and the last one here will be AD. So how do we get AD is A11 A, and then our D is based on here, so this is a D and a. Okay, so here is our simplified Boolean equation for a 4-input K-map. So let's look at some rules to help in getting the correct simplified Boolean equation. So rule number 1, group only the ones. Okay, we are not supposed to group any zeros, so here is wrong because here we are grouping 0 here, so here is wrong. So we only allowed to group the ones, and remember power of 2. Power of 2 group. Okay, so 2 is 2 to power 1. Okay, 2 to power 1 equals to 2. Rule number 2, no diagonals. So we are not allowed to do this. This is a diagonal, so it's wrong. If you have a diagonal, what you need to do is you're only allowed to perform like this, and overlap is allowed. Okay, overlap is allowed, but diagonal is not allowed. So group of 3 groups not allowed. Not okay, so here is also 5 groups also not allowed, something like this. So this is okay, and this is okay. Maximize the loop size. So if we have a multiple ones in our minterm, so we need to see how we can minimize the number of loops, therefore making the loop as big as possible. So in this case, we can see that we can group them together 2 by 2, but this is not optimum. Not optimum. Okay, the final F, not optimum or most simplified. It's not the most, not most simplified. Okay, the final F, okay, not the most simplified. So to have a simplified, the most optimum Boolean equation F, we need to take the biggest loop. So in this case, 4 and 4, and here in fact we're going to get F is equals to A bar plus this is 0 1. This is going to be B. Okay, so here is F equals to A plus B, and in this case it's going to be F is equals to this one plus this one plus this one. Okay, and the first one there is going to be A bar B bar plus A bar B plus AB. Okay, so here we can see 6 literals. Okay, 6 literals here, and here is only 2 literals. So if you don't take the largest loop, it's still correct. You're still going to get the correct F, but it's not going to be the most simplified form. Loop must contain only ones. Must contain all ones. Okay, so for example here, if you do like this, not in group. Okay, this is wrong. Okay, so every minterms, okay, every minterm should be in a group. So in this case, we have no choice but to group him by itself, just the one. Okay, so what is our F here? So our F here is simply going to be this one is A B bar C plus A bar and B. Okay. Groups may overlap. So the groups may overlap. So for example here, this one is better. Okay, this one is better. So here in fact the better solution is to overlap like this. Okay, so we have a more simplified equation, because for example, if you do like this, you are going to get F is equals to, this one is A B bar C plus A B C bar plus BC. Okay, so this one, for this one, we are going to get the first one there is F is equals to BC plus AC plus AB. So you can see this is better. This is not it's correct. Okay, the F there is correct, but it's not in the most simplified form of the Boolean equation. Rule number 7. Okay, rule number 7, the groups may wrap around. So for example here, in this case, we can do something like this. Okay, we can wrap around like this. So obviously we are going to get a much better, more simplified Boolean equation by using the wrap around. So here also we can wrap around rather than taking like that. Okay, so in the wrap around, for example, in this case we have two groups. Okay, two groups only. Okay, and here we have 1, 2, 3, 4 groups. Okay, so here we're going to get 4 terms, 4 product terms. Here we're going to get 2 product terms. So just quickly do this. We are going to get actually B bar C plus A bar B D bar. Okay. Okay, so here's the solution for this one. We have two product terms. Okay, so let's move on to the rule number 7. Sorry, this should be rule number 8. Rule number 8. So rule number 8, fewest number of groups possible. Okay, fewest number of groups possible. So here we have 1, 2, 3, 4, 5. This is 5 groups. Okay, and here we have 2 groups. So remember, one group is equals to one product term. Okay, one group is equivalent to one product term. What about don't care? So if we have a don't care in our K-map, if we have a don't care, so a don't care condition. What is a don't care condition? So can be either logic 1 or 0, or logic 0. So both works. So for example, this x equals to 1 to maximize the loop size, x equals to 0 to reduce number of loops. So for example, if we have something like this in our truth table, okay, whereby your truth table will look probably something like this. You have and so on. So our output F, okay, so for 0 you have 0, 0, and then for 0, 1, 0 you have a 1, and here you have x. So if in the truth table, you have an x here for 1, 1, 1, which is this one. Also, okay, so in the truth table, if you have a x in 0, 1, 1, we can choose to be 0 or 1. So we can choose. So do you want to make the x as a 0, or do you want to make the x as a 1? So in this case, the best scenario is by making x equals to 1. So if we make the x equals to 1, we therefore can group these 4 together and get here f is equals to b c bar. Okay. And for this one, we're going to take this to be 0. So remember x there, we can choose to make it either 0 or 1. So we're going to make according to what is advantageous to us in getting the minimum form. So if you take x equals to 0, and therefore we're going to get this one. Okay, so the first x will be 1 and the second x will be 0. Okay, so let's look at the K-maps for max terms. So we can also do a K-map for max terms. So for example, from the TT here, the truth table, we can get our 2x4 K-map. And you can see here, okay, we just transfer these numbers into the K-map, and eventually we'll get f equals to AC plus BC bar. Now we can also take a 0. If we take the 0, so for example here, if we take this 0, okay, we are going to get the product of sum or the POS form. Okay, so here is POS and here is our SOP. So in the POS form, this term here, the first POS term there is going to be, this is not common, so it's going to be B plus C. And the 0 here, there's no bar. Okay, the 0 that is actually no bar. As you recall, in POS, if it's a 0, it's a no bar. If it's a 1, it's a bar. So, and the second term here, we are going to get this 0 here. So it's going to be A plus C bar. Okay, which is this one. So in the end, our POS term is simply going to be A plus C bar and with B plus C. And that is our SOP for from the Karnaugh-Map. And it can also be extended to, it can be also extended for to 4 input. Okay, 4 input, so we can derive what is the minimum Boolean expression for a 4 input in the POS form rather than SOP. Okay, so that's all for our lecture for this week, and we'll continue with the next topic next week.